good, because it's not going to be the 81 most extra 45 minutes of your life. Last week we talked about um yeah, talked about power series, and we concluded that basically when power series an x minus a power of n is convergent in a segment I, interval I, then it is uniformly convergent in a very closed subinterval of I. Moreover, the series of derivatives and the series of anti-derivatives are uniformly convergent as well. Meaning that, oh, still, what's up? Get out. Whatever. Meaning that well, I'll take the basically word we put here. We can basically differentiate and integrate element by element. How many times we need when it comes to a power series. So, as we mentioned before, and now here it comes. This week, lecture number 18 and 19, we discuss the subject of Taylor series, Taylor expansion, whatever. Taylor is first name was Brooke Taylor. It's the name of a boy band member, but he was a mathematician. He died a long time ago. And the question is that, as I already mentioned when we finished lecture number 17, what we mainly done when we talked about the connection between a function on one side and the power series on the other side is using the fact that the power series equals some function to calculate sums and stuff like that. I mean, knowing that the sum of xn is 1 above 1 minus x, we showed some examples. Okay, we differentiate element by element, multiply by x, and the bottom line is we can use this equation to calculate some sums. And the direction of the equation is we know that the series equals the function. Now I want to talk about the other direction of the equation. How can it be useful that a function equals some power series? Now, at first look, it doesn't look very useful. I mean, the power series is like infinite sum. It's more complicated than just a function. But as we will see today and on Tuesday, Bezrat Hashem, the fact that the function can be expressed as a power series, moreover, we know how to find this power series, is very useful. Now, okay, I need to. Oh, it is recording. Because It is recording right now. Okay. There are two questions. The first one is given a function, how can we know that it equals to some power series? And the second question is how if it does, how can we find this power series and what are we going to do with it? I want to start from the second question. We'll talk about the first question on Tuesday, how in the beginning, we know that a function actually equals a power series. But we know that the power series can be differentiated how many times we like. So the basic condition for a function to be equal to some power series is to be infinitely differentiable. I mean, we can differentiate it how many times we want. So let f be infinitely. I write this. That's right. Infinitely differentiable. I mean, fn, the derivative exists for every n. At some point a. Now, as I mentioned, we will see it on Tuesday. It is not enough. There are infinitely differentiable functions at some point a that are not, you cannot express them as a power series. So right now we assume that f can be written as a power series. Not for every x on R, not for every real number, but at some interval I around a, the point a. I mean, the geometric series is the function 1 above 1 minus x, not for every real x, but around the segment between -1 and 1 around 0. And we discussed this assumption on Tuesday. How can we really tell the function equals some power series? Now, we can find this power series, meaning that we can express the coefficients an using f in that way. Let's write down, first of all, explicitly. Of the basic rule of sigmas. You write it without a sigma, and it is, I'm not saying it's easy, but it is less complicated. A1 plus A2 x minus A squared, A3 x minus A cubed. I have the place and time, but let's not exhaust ourselves. 2A4 x minus A to the power 4. Starting easy. How can we express A0? Yeah.
Sorry, I don't remember. A sub n and A are connected in some way. It does like an converge to A or what?
No, nothing.
Okay.
Nothing. N is a real number. An is some expression of n. More precisely, that is independent of x. You can say n, it can be a constant, but it's just notation.
What do you mean independent of that?
Without x. It can be an expression of n, it can be a constant, but an cannot be x to the power of n or something like that without any x.
Okay.
So, how will you express A0 using f? Any ideas?
Um,
A0. to begin with.
Where x equals a.
Yeah. If we put we have fa is a0, and it's an equation. It works both ways, but let's write it down explicitly. A0 is fa. Marvelous. We found one coefficient out of infinity. Zero progress. But you tell me, how can we express a1 using f? Exactly. Now, we know that we can do that. On one hand, we assume that f is infinitely differentiable. On the other hand, it's a power series. We know we can differentiate it element by element as many as we want, any times as we want. Now, differentiate, and he gives us f tag x is a1 plus 2a2 plus 3a3 x minus a squared plus 4a4 x minus a cubed, and so on. Now again, we put x to be a, and we have f tag a is a1, meaning that a1 is f tag a. Brilliant. What about a2? How can we express a2 using f?
So we differentiate again.
Yeah, and again. Again, differentiate.
What is the first part from the right or right thing? What we say the first part from the right or right? Yeah.
I'm not familiar with this expression.
It said that there's like one expression in Hebrew, where it's like you don't derive to like don't derive to like everything you see on the exam. You know what I mean?
No.
Uh,
The answer is no. We have 2a2 is the second derivative, meaning that a2 is actually not the second derivative, as one can think from the first two cases. It's f two tags above 2. And for my last magic trick, we differentiate again. We achieve f3 tags, 6, a3, next one say bye-bye. It's 2024. And when we put x to be a, we get that f3 tags at a is 6a3, meaning that a3 is actually f3 tags above 6. Now 6 is 3 factorial, and generally one can see that an is the nth derivative at a above n factorial. So we have the following conclusion. If we know that f is a infinitely differentiable and b equals a power series, then the power series must be the nth derivative of f at a above n factorial multiplied by x minus a to the power of n. Now we call this expansion of function as a power series to be the Taylor expansion or Taylor series. This is the Taylor expansion of F around A. Specifically, how do we write it? With E?
Yeah.
Specifically like that? Whatever. Specifically with two L's, probably. Specifically, when A is 0, we get the following expression. X above n, and it is called this specific case is called the how do I use his name? Maclaurin?
Yeah.
With two double C, like? Probably that, yeah, I think so.
I think.
It is one C, right? No, it's a football American player, no. McLaurin serious. No, it's actually with A between the C and the
Yeah.
what the hell?
McLaurin.
McLaurin. But he was Scottish, as far as I remember.
Find some interesting things. Math person. About French. From McLaren.
What?
What?
Expansion. Oh, now there are infinite, uncountable. None of you know what that means. Infinite real numbers. Somehow Maclaurin choose a number and got its own name for A equals 0. But as we'll see, most of our examples are going to be around 0, so it's good to have a specific name for that. But we'll use Maclaurin and Taylor all the same. Okay, so now we know that. Notice that. Do I want you to notice it right now? That's a nice question.
We wait until the end of the class to see if we notice it by ourselves.
Notice that the Taylor expansion around A is unique if F equals some power series around A, it must be the Taylor expansion, as we calculated. If infinitely differentiable function F equals power series around A, it must be the Taylor expression series. So first of all, we can use this fact, and that's questions lecturers like to put in the final exams. We can use this fact to calculate derivatives or high order derivatives of function f at A. For example, we know that, and right now it's our only main example. We've already achieved some other examples using this basic one, but we know the geometric expansion, x to the power of n. So here, AN are all 1. Coefficients in the series are all 1. On the other hand, the function 1 above 1 minus x, let's call it f, is infinitely differentiable. 0. And this is in the series is a power series around 0 that equals the function. You know the first case? Yeah.
So the only two cases where this works is either when we have a infinite polynomial or the power of x is negative.
I do not follow. What?
So it has to be infinitely differentiable,
Right.
which it means that it can never be 0, because if it's 0, it's not a differential anymore.
No, why? 0 is differentiable. It's a constant. I can't work, for example, with the denominator that eventually is zeroed somewhere in my interval.
But if
I don't
it's
know, piecewise function. Non-differentiable. Absolute value at 0.
no, yeah, but I mean, like, for example, on the first example you gave, you differentiated and one term just disappeared because it went to 0. Right? Ah, no, it didn't go to 0.
What?
No,
1
no,
above
no,
1
no,
minus
no,
x?
right, no, the one before 98. I got confused now. So, can you go up a bit?
Yeah.
So in this case, when you differentiate it enough, the terms like go to 0 and disappear, or what happens?
Yeah, but on one hand, we have the function f,
Yeah.
which is still there. And on the other hand, the series is an infinite sum.
Yeah. That what I was saying is because it's infinite, you can derivate as much as you want. But if it
Yeah.
wasn't infinite, is it not infinitely derivable? Because
Oh, it is just 0, 0, 0, 0, 0.
and that's fine.
Yeah.
Okay.
I mean, the only case it happens when it comes to polynomials that are a finite power series, finite series, but it works fine, just fine. So on one hand, we look at the series, we see the coefficients are 1. On the other hand, but what we explained here, we know that the coefficients are the nth derivative of f at 0, because that's the point A here, above n factorial. So we get that 1 equals the nth derivative at 0 above n factorial. And so the nth derivative of the function at 0 is n factorial. For example, instance, the 2026 Happy New Year derivative of this function at 0 is 2026 factorial. Now, legit question is, this is the function. Hello, very nice. Calculate the 2026 derivative of the function at 0. Now I'm going to differentiate it 2026 times. Now I'm going to find the Taylor expansion and compare the coefficients in order to understand what this derivative is. Of course, it can be more complicated. Some function that's not one of our basic functions. Right now we have only one, the geometric expansion. Right away we're going to have another two. But this is a reason, something like that, to look at the equation function power series from the other side. Not using that the power series equals a function and calculating sums or something, but the other way around. We know that the function equals the power series, and we use it to calculate something about the function, not about the power series. It's not the main reason. It's not the main answer to the question, why is it good the function equals the power series, but it is an answer, and it's the right place to show it, so why not? Okay, any questions? So, we know that the function 1 above 1 minus x equals this series in the segment between -1 and 1. I want to show you another examples that you can probably use freely whenever you need, where functions equal power series. Now, we still assume there is an assumption behind the scene that the function equals a power series, and we're gonna discuss this assumption, as I mentioned, in our next lecture. So examples, we start with the simplest example, probably the function e to the power of x. And as I said, most, if not all of our examples are going to be around 0. We know how to calculate the derivatives of e to the power of x. It's pretty easy. For every n, the derivative of n to the power of x is just e to the power of x. So when we put x to be 0 here, we just get 1 e to the power of 0. And then the Taylor expansion, or more precisely, the Maclaurin expansion of e to the power of x is just 1 above n factorial multiplied by x to the power of n. A legitimate question is for which x's? I mean, we know that this equation holds for every x in the segment between -1 and 1. But for which values of x this equation holds? No, it's a power series, and we can calculate its domain of convergence pretty easily. For what values of x? Here, n is 1 above n factorial. So the radius of convergence is 1 above the limit and goes to infinity of n plus 1 and an. You know what's going on here. The limit of one above n plus 1 factorial, 1 above n factorial. We know how things cancel each other. We are left with, let's do it a bit slower. It's n factorial, n plus 1 factorial. We are left with 1 above n plus 1, which is 0. So 1 above 0 is infinity. which means that domain of convergence is every x, every real number x. This is just R. You can write it down. Side here with R. Boop. Yeah.
So what you're doing here is you know the differentiation after n times, and that's what e to the x is in like equals the sum. And then like when you perform the sum, it's 1 over n factorial, which is how every Taylor series is, and then you have
No, every sorry, yeah. Every Taylor is with one the derivative, the nth derivative above n factorial. Specifically, when it comes to e to the power of x, all the derivatives are just one. Because every
Okay,
derivative. So we are left with one above n factorial. But yet again, we assume that the function a to the power of x equals a power series of around 0. And then necessarily it has to be the Taylor one. But then again, next lecture, we talk about this assumption. How can we know the function equals a power series?
Why do we set a n to be 1 over factorial, n factorial?
Generally, an is the derivative at 0 above n factorial.
Oh, right, yeah, sorry, yeah, okay. Great.
Um,
And then I remember we did the, like, this thing last lesson, but I forgot why it makes sense.
this one R, calculation of R.
Yeah, I remember we did
Um,
it. Can you just remind me why it works?
Yeah, 2 weeks ago, we looked at the power series, general configuration of power series, and we applied the ratio test.
Right.
Concluded that it has to be convergent. The limit of the ratio test is smaller than 1 when we talked about in the using the language of Radisson convergence, we concluded that the Radisson convergence must be this number or 1 above the limit of the nth root using the nth root test. We had 2 equivalent formula to calculate R.
But if the range of convergence isn't right, because the range it isn't the number.
Yes.
I just thought when I saw infinity, I thought instantly diverge.
Yeah, but it is the radius of convergence. So when R is infinity, it means that it converges everywhere.
What does that mean?
When
This means that for every value,
any value of x you put here,
because
you'll
because the range is infinite.
yeah, you'll get the radius is infinite. You'll get a convergent series, and moreover, I claim that it is convergent to e to the power of x. I mean, for example, right now you can calculate the sum starting at 0 and never ending. A number you like?
2025.
Mm-hmm. When we're young and beautiful. The young and the restless.
I swear.
It is e to the power of 2025, for example.
Really?
What? Yeah, it is for every number x. It works.
Oh, right, yeah.
So specifically for 2025. So this is e to the power of x. I want to show you another example. Let's start You prefer sinus or cosinus?
Cos.
What?
Oh,
Okay. Yet again, at a equals 0. For every n, what do we have? It's not very hard to calculate derivatives, but it's not as simple as a to the power of x.
you can agree with mine.
What?
He said that it's going to blow my mind.
You can blow your mind.
I mean, I know you can express that to Taylor series, but
What, the cosinus?
Just wait, just wait.
Just wait for it, Thomas. Okay, the first derivative is minus sinus. Second one, however, is minus cosinus. Third derivative is sinus. And what do we have here? The fourth derivative is cosinus again. So it's not the same derivative at every step, but we do have a nice cycle. Cosinus minus sinus, minus cosinus, sinus, cosinus minus sinus, minus cosinus, sinus, again and again and again and again. Now, we put 0, yes, that's our point A, and so on. One can say that generally, it's 2L probably. Generally, it will generate something like that.
Yeah.
With 2L, right? When you differentiate, I don't know, 4K plus 1 times 1, 5, 9, 13 times, you get minus sinus. And when you derive 4K plus 2 times, 2 times 6, 10 times, so on, it's minus cosinus. 4K plus 3, 3 times, 7 times, 11 times, it's sinus. And when you differentiate 4K times, you don't differentiate at all, 4 times, 8 times, 12 times, you get cosinus. At a equals 0, we get that every odd derivative of an odd order is 0, be it sinus 6, be it minus sinus 6, it's 0 nonetheless. So one can write it as, you know what, let's write it down explicitly. Is 0 at sinuses. It's minus 1 at 2, 6, 10, etc. And it is 1 at 0, 4, 8, etc. In other words, the derivatives of odd order are just 0, while the derivatives of even orders are minus 1 and 1 alternately, whatever you say. It's 1, minus 1, it's 1, minus 1. So in conclusion, we have cosinus 6 to be the sum of minus 1. I changed the letter from K back to N. Only the odd. I mean, you can write, let's do it. Slowly and steadily. This is generally the general Maclaurin expansion. Now we can write it down as the sum of the odd parts and the sum of the even parts. This is 2n plus 1, which is 2n plus 1. 1. And here it's 2, 2, 2, n.
Well,
Ah,
you can say this because it's an infinite sum, so saying like n and plus one.
what?
Yeah, because it's an infinite sum, we can just say f to the power of 2n plus 1, even though it's like because we're multiplying, it's bigger than the index of the sum, but because it's infinite, it doesn't matter.
No, it's simpler than that. I mean, you have a sum. Let's say you have eight numbers. I can divide it into two different sums.
Yeah. I'm just saying, we're going to every index of the sum, even though we're multiplying because it's an infinite sum. That's what I'm trying to say.
I don't fully understand.
That's not.
Okay. I mean, we've just practically divided into two sums, one with the odd indexes and one with the even indexes. And the coefficients with odd indexes are just 0. And here we have -1 to the power of n. So one can conclude that the Taylor series of cosinus is -1 to the power of n, blah, blah, blah. We can answer the same question for what values of x. Now, this is the point we discussed earlier, not today, some last week or the week before that, that formally speaking, we cannot use the ratio test here because every second coefficient is 0. We cannot, the limit doesn't exist. We cannot divide by 0. But on the other hand, if we technically look at this coefficient as all the coefficients, and we use 2n and 2n plus 1 factorial, using it to calculate r, we'll get the right answer. I just want to say that similarly, now the formal calculation, similarly to the previous example, the domain of convergence is all R. For every point x you put here, x to be 200, pi, you name it, this equation holds. And yet again, with the assumption that cosinus equals some power series around 0. So right now, yeah.
No, let's just say, this is the way calculators do cosine and sine, right?
That's a good question. And I'll talk about it later. I don't know if we'll make it today or Tuesday, but we'll discuss it. The actual important main use of Taylor expansions. Any other questions? So, right now we have like just like in Pokemon, 3 starters. We know that the geometric series equals 1 above 1 minus x, and vice versa. I mean, the equation goes both ways. And as mentioned, it is important to acknowledge it. E to the power of x and cosinus. You chose cosinus, your own fault. Each one with its own domain of convergence. left has between -1 and 1, two others for every x, real number x. And we can use all three of them, or at least try to use, in order to answer questions like the questions we already ask ourselves. I mean, here is a function, not one of these three, yeah. Let's find a power series equals to this function. Let's calculate a sum. Let's, I don't know, find some derivative, what we show today. We can use not only 1 above 1 minus x, but also e to the power of x and cosinus x. So we can use all three of them when we answer questions like, here is a function, find its Taylor expansion or Maclaurin expansion, whatever, or calculate the following sum, etc., etc. Let's do some examples, okay? For example, and here we'll do it later on. Examples, let's start with a simple one. Find power series such that sinus x is the sum an x to the power of n. Now, assuming that sinus x does equal some power series around 0, we know that it is the Maclaurin series, and we can walk through the same process we did with cosinus. But first of all, without this assumption, we cannot do it. And secondly, even with this assumption, we can do something easier. We know that yeah, but who? Exactly. You know that cosinus equals some power series. And as we mentioned when we started this class, and we discussed it full roughly in lecture number 17, we know that when it comes to power series, we can basically differentiate, integrate how many times we like, whatever we like, and differentiate element by element. We get, on one hand, it's sinus x, on the other hand, it is to the power 2n that in Hebrew we say jumps out. To the power of 2n minus 1. And using the fact that 2n factorial is 1 multiplied by 2 multiplied by blah, 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 multiplied by 2n minus 1 multiplied by 2n, we can go to the next step. 2n and 2n downstairs cancel each other, and we are left with 2n minus 1 factorial. Notice that it will be more precise to write it down a bit differently. I mean, here for the index n equals 0, we get x to the power of -1, which is of course not part of the series. So yet again, first of all, one can integrate and not differentiate, which is more safe. But when we write down the sigma explicitly, and we actually get 1 for n equals 0, and minus x to the power of 2 around above 2 factorial for n equals 1, and x to the power of 4 above 4 factorial, minus x to the power of 6 above 6 factorial, and so on. When we differentiate it that way, we do get minus x plus x to the power of factorial minus x5 power of 5 factorial, and so on, which it is minus sinus because it is the derivative of cosinus. And so we get that sinus x is minus plus, right down. Other way around. And write it down that way. Sinus x is the sum of what? Yeah. I'm afraid. As they should be. The road to the orgasm is harsh. Only the most excellent of students can walk through all of it. So we have sinus. Any questions? So let's give it another example. We did something like calculate the sum of n squared to the power of above to the power of n. Remember? And
Yeah,
we
just a question.
yeah.
Because the signs are flipped, shouldn't it be n plus 1 or n minus 1? Like n minus 1 to the power of n minus 1 or something in this case?
No, because when you put n equals 0 to get x to the power of 1, you want it to be positive.
Right.
So it should be minus 1 to the power of 0, not 1 or minus 1. And we used the geometric series. We differentiated, multiplied it by x, differentiate again, multiply by x again, in order to get n squared n power of n, and we put x to be half. 5 steps in order to calculate this sum. I want to show you a different one, a bit trickier, if you want. Calculate the following sum. And one above 2n squared, and that's it. And factorial, and that's it. Question is, in the first example, the question of who should we start with wasn't very difficult to answer, right? We see sinus. We are familiar with 1 above 1 minus x, cosinus, and e to the power of x. From these three, who is the most, I don't know, similar to sinus 6, but probably cosinus. So we start with cosinus. Right now, we probably are not going to use the geometric expansion. It doesn't have factorial in it. But on one hand, it reminds us of cosinus. The problem is that cosinus has minus 1 to the power of n in its numerator, not 1. On the other hand, it looks like e to the power of x, but the numerator is 1. But here, the denominator is n factorial. and not 2n factorial. So the question here is, where do we start and how do we overcome the obstacle in our way?
The problem with the cosinus one is that because it's x to the 2n, you can set x to -1 and solve the problem.
Yes, I mean, I can set, but it will not solve the problem. Yeah. To put if it was x to the power of n, he says, you know what? Put x equals -1 and you solve your problem. But here, putting x to be -1 or every other x will not get rid of the -1 to the power of n in the numerator. As I said, it's a bit tricky.
Can you set the second one, the x plus the second one to something that goes to 0 every second index?
No. X is a constant. You put one x, you stay with it forever.
Yeah.
Yeah.
Oh,
So again, we have some. It's not so simple deciding who to start with. And of course, it's connected to the next question. How do we march forward? So as I say, it's a bit trickier. Any ideas? More ideas? Before I show you my answer, at least.
Model,
Huh?
model.
Like how?
Something that can be like model plus 1.
Yeah, I mean, if we put x to be 1, we are left with -1 to the power of n above 2n factorial.
Yeah, but then we model.
the modulus.
Sorry, the absolute value.
Yeah, but the absolute value of the sum is not the sum of the absolute values.
I mean, cosinus seems the one that's closest, but at the same time, the hardest to
Yeah.
find something that works.
First of all, let's write it down explicitly. It's 1 plus 1 above 2 factorial plus 1 above 4 factorial plus 1 above 6 factorial, and so on. It is definitely easier to look at it that way. Now, cosinus is tempting with its fat, nice 2n in the denominator, but it is not the way. Yes.
Oh,
As
oh.
Ugandan Knuckles once said.
It could be like
As
the
Somaliland Knuckles once said.
it could be e to the 1 minus sine to the 1, sine 1 or something like that.
You are getting closer. Right. Yes. Now, we know that when we look at e to the power of 1, which is a good numerator but a bad denominator, we have, let's write it down with a dot. It's without the dot. We have 1, and it is 1 again because it's 1 above 1 factorial, plus 1 to the power of 2, plus 1 above 3 factorial, 1 above 4 factorial, 1 above 5 factorial, 1 above 6 factorial, and so on. What can we add? What can we do with these series in order to get rid of every second of every odd index?
Take out element 1.
E to the power of -1. This is the correct answer, as far as I understood what you said. If we look at e to the power of -1, well, every odd index should be with a negative sign, while the even indexes stay the same. And when we add them up, we get a nice little fancy tricky thing. It's not our sum, but it's 99% of it. It's 2 times the elements of the even indexes, and the elements of the odd indexes cancel each other. So our tricky sum equals e plus e minus 1 above 2. Are you familiar with the parabolic functions?
That's in that page.
It's cos or cosh, we call it. It's a cosh 1. One can just speak about cosh x, which probably be this sum with x to the power of n. But it's not important. Don't discuss these functions here, and we are totally fine. So here is a function. Find the power series that equals this function without calculating all the derivative in an exhausting process. Here's a sum. Calculate the sum. Find the derivative of some very high order. Every question can be asked and answered not just about the geometric function series, but also about e to the power of x and cosinus x. I'm not saying she's a gold digger. I'm not saying that you'll never need to calculate using your hands the coefficients with the derivatives in Taylor, but most of the time we are not engaging with calculating the coefficients an with the nth derivatives. No, we use a function that we already know what its Taylor series is, and we differentiate, integrate, multiply by x, changing the indexes somehow, whatever you like, in order to achieve our function. Okay. Any questions about that? So, to my last point for this lecture. Let's start. The main reason to use Taylor and its importance, the approximation, Emancipation Proclamation, approximation using Taylor. Expansion. Under our assumption, the function is on one hand infinitely differentiable, and on the other hand equals some power series functions. We can write the function in the following way. Calculate the sum to some index n. Oh, they're plotting. And the rest of the sum. We are familiar with both sums. One is the partial sum, and the other one is the remainder. We denote the partial sum with p and x, that's big P. It is the Taylor polynomial of order n around F, around A of F. We already know that the rest of the sum, the infinite remainder, is denoted with Rn. Well, now, right now, it depends on x. For every x you put, you get a different series with a different remainder, so it's Rnx. Now, we can say that f can be approximated using the Taylor polynomial. The better, the greater, and the greater the n, the better the approximation. Approximation. What is a better approximation? The remainder is smaller. Yeah.
From n for this like 1 to infinity, wouldn't it be the lesser the n, the greater the approximation? Because there's
No, I'm using the polynomial.
Oh,
Yeah. I mean, I don't have an infinite number of seconds to calculate something.
yeah.
So it's the polynomial. More precisely, let's write it down. No. More precisely, the what we call error, which is the absolute value of the, let's write it down explicitly, the absolute value of the remainder is smaller. Now, I'm not saying that this is the only way or what actually happens today in 2026, but as you mentioned before, and it is an important one, let's say I want to calculate cosinus 1, e to the power of 2, pi, square root of 2, whatever. I'm using a calculator. No matter how strong, how efficient your computational abilities are, you still have a finite number of bits at your computer. I mean, I'll rephrase it. Cosinus 1, for example, is an irrational number. You need infinite number of digits after the dot to express it. Now, use every server around the world, every smartphone, every computer, every Dyson, iRoomba, vacuum cleaner, whatever you want. Use every chip that they manufacture in Taiwan from this point till the end of times. It's a finite number of bits. You cannot fully express cosinus 1 or e or pi. So, what do we use? Approximations. Now, how good the approximation should be is not, or at least not purely, a mathematical question. Let's say my approximation and the real number has the same 3 digits after the dot. Is it good? I don't know. I mean, if say I want to build a football. Football means soccer. A football field. It should be, let's say, 100 meters. If it is 100 meters and 2 millimeters, it probably checks out, right? But let's say I'm a brain surgeon and I miss the specific point in the brain I'm right now working on in 2 millimeters. It can be harsh, right? So 2 millimeters, 0.002 is good error or bad error. It's not a mathematical question. It's a question about the reality. Whatever you want to do, that's what you want to say. We need to know how to answer the following question. On one hand, given some n, you're sitting at a desk, your Indian boss comes, we can calculate only 20 steps. How good or bad the approximation is. Yes. Tell me what the remainder is, or at least give an approximation of the remainder. And on the other hand, your boss can come and say, you know what, we're building a bridge. We are calculating how much we are getting from the left, how much we're getting from the right. We cannot miss both sides more than, let's say, 1 centimeter. How many elements in the polynomial you need to calculate in order to achieve this kind of remainder that is so small, 4 centimeters or something like that. Now, our question, and the main question, yeah, and vice versa. You are coming with the digits. I want an approximation that is working fine for the 4 digits. The 4 digits of E and the polynomial you calculate for E should be the same. How many elements in the polynomial you should calculate? The main question has 2 parts. Given an n, the number, the word in Hebrew is leha'arich. No, with A, with Aleph, with Ain. To evaluate, yeah. It is the right word, but
what do you want to say?
I mean, we're not going to precisely find the remainder. It is an infinite sum. So it's yet again, it's approximate. We should find, I said explicitly what I want to see. We should find an upper bound to the error, the absolute value of the remainder, but we cannot just say no million, probably million. It's an upper bound. It's going to some not the tightest one, but kind of tight. Given an n or n big N, how can we evaluate? I'll use this word nonetheless. Evaluate the error. Meaning is IE, right? Finding an upper bound, a good upper bound. For the error. And the second part, let's write it down that way. Okay, and B, we are given a real number M, and how can we find the minimal N such that the error is smaller than M? It can be asked. for a specific value of x or for every x in some interval. All right, and then for example, that would the answer. That's example of the question. Calculate e to the power of 1, let's see. With error less than, I don't know, 110. So we need to find, so firstly, we need to find the specific n that gives us the remainder is smaller than 0. 1, because we are talking about to the power of 1, right? No, 0. And then calculate the partial sum. I mean, we can say that E is the sum of 1 above n, which is 1 plus 1 above 1 plus 1 above 2, and so on, till 1 above n factorial, and then the remainder at 1, because we put x equals 1 here. Now, for n to be n equals, for example, 2, the following polynomial is that till n equals 2, you get 2.5, which is not, of course, it's not e, but the remainder between e, difference between e and 2.5 is still larger than 0.0001. We can try and fail until we succeed, find the exact n that works. But I want to show you, and probably going to be on Tuesday, I want to show you how we can find this n without trying until we get to the right approximation. I mean, it can be n equals 10 or 100 or something like that. We cannot calculate 97 elements. No, it's not enough. 99 elements, not enough. Oh, 100 elements. Finally, do the job. On the other hand, the simpler way to put it, the first side of my question is, you know what? I give you n. N is 10. Now we need to approximate, or as I call it, evaluate, finding an upper bound to the remainder. And the question is, this is example for the question, right? The question is now, how do we answer this question? So, how can we find a nice, firm, good, I'm not saying tight, but good upper bound to the remainder? I divide my answer to 2 parts. And I don't know how much Erez talked about it in the first course. When I teach Infi 1, I usually try to talk about it a little, just, in order to prepare the ground, as we say in Hebrew, for Infi 2. But in order to answer these questions, 2 parts of my question, we need a nice closed formula for the error / the remainder, or at least for an upper bound. I mean, it's not true, but if one could say, you know what? Always, 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 the upper bound for R and X is 1 above N. So be like, oh, okay, this is 1 above 10,000. So we need to calculate 10,000 elements here, and the remainder will be smaller than 1 above 10,000. It is not true to say that the remainder is bounded by 1 above N, but it is true to say that it's bounded by something else. By what? We already finished, almost finished. We're going to see on Tuesday, but I just want to say that we will divide our answer to, yet again, 2 parts, 2 alternating series, minus, plus, minus, plus, minus, plus. It's pretty easy there. And the general case. But how do we do it? And our next other question, why does a function equal power series and etc.? As you see the clock, we'll talk about it on Tuesday. Okay, any questions? Okay, so we can finish.